Is my screen visible, sir?
Yes, please proceed and please stick to the timing.
Okay, sir. A very good afternoon to all. I am Ruby Mishra from NIT Rourkela, Odisha. I will be presenting the paper titled FPGA-based high-throughput substitution box architectures for lightweight block ciphers. Co-authors are my supervisors, Professor Manish Okade and Professor Kamalakant Mahapatra. So this is the outline, introduction, motivation, and then I'll be discussing regarding the general architecture of lightweight ciphers, then the proposed S-box architecture, then we'll discuss the implementation and results, and then I'll conclude with the future scope. So recently, the design and implementation of encryption algorithms, both on hardware and software platforms, has been quite significant in the research domain. Basically, a dedicated hardware definitely improves the performance of crypto algorithms for a specific target applications. So mapping an algorithm to a optimized hardware is a crucial task which has to be taken care by the design engineers. Basically, the hardware implementations can be carried out in two approaches. That is, either we can go for FPGAs or ASICs. FPGAs are field programmable gate arrays. Basically, for prototyping our designs, we use FPGAs, and it is a faster method of bringing the concept to hardware. And if we go for application specific ICs, these are custom ICs. Which need to be carefully observed by the designers, and before fabrication we have to take care about the optimization as well as the security aspects of the design, which opens the area for hardware security in this aspect. So the target is to design a compact and high throughput architecture for target applications. And we have chosen symmetric lightweight primitives because it occupies less area and performs well in terms of area, throughput, power, etc. So the motivation behind choosing lightweight algorithms are we have seen that there is a significant surge in the demand for IoT based consumer electronics, and there is also a thirst for computation anywhere and at any time. So coming to the requirement of these IoT devices, we want that the device should be smaller in size. Only then it will be mobile or portable. Device should communicate with each other in the IoT environment, and also with the user. It should talk with the user so that we can call the device to be a smart device. Again, for this, we need a connection, and the choice is a wireless connection. Also, we want that the battery life of the device should be longer, and it can be achieved only if the power consumption is optimized. So apart from all these requirements, we also know that the devices deployed in the IoT environment are continuously involved in handling sensitive data. So this raises the concern for privacy and security. And keeping all these things in mind, the conventional crypto solutions may not be suitable for IoT devices, and hence this has led to the emergence of lightweight cryptography, which we'll discuss further. So the design considerations for lightweight block ciphers are, we need to choose or design the lightweight block cipher in such a way that they should provide security which is sufficient to the target applications. So if we consider the research domain, we can either alter and analyze design, or optimize an existing cipher, or develop a completely new cipher. We have in this work, we have optimized an existing cipher. In order to evaluate the lightweight block ciphers, we evaluate in terms of area, power, throughput, and energy. And it depends on the factors like the individual architectures of the submodules present in the encryption algorithm. And it also depends on one of the crucial block, that is whether it is a substitution permutation network style or whether it is a Fichter structure style. Then the dependency is on the frequency of the clocks, which is used to drive the circuit, because it affects the performance of the circuit. Then comes the key scheduling process, which differs from algorithm to algorithm, and it solely affects the performance of the design. Again, for area consideration, we need to keep in mind the block size and the key size of the encryption algorithm. In this work, we have chosen clean, Midori, and gift lightweight ciphers for evaluations. Now coming to the general architecture of lightweight ciphers, we have chosen a 64-bit data path, and here the input plain text is of 64 bits along with the output ciphertext. We have a internal module that is a key scheduling module, but the key bits are different as mentioned here for the individual ciphers. And we have the another internal module that is the substitution permutation network, where the substitution layer is a nonlinear layer and the permutation layer is a linear layer. We have focused on the substitution module because it comprises of the S boxes, and these are crucial for security as well as for the performance of the ciphers on hardware platform. Again, this process of mixing of plain text with the key bit along with passing it with the SP module occurs for a certain period of time called as round operation, and the number of rounds are stated in the literature of these algorithms. And now coming to the design considerations for the SBox module, as I said, we have focused on the SBox, the nonlinear SBox model. And here for a 64-bit data path, we have 16 SBoxes. And in most of the lightweight ciphers, we have 4-bit SBox, that is 4-bit input and 4-bit output. And this is more beneficial in terms of area and delay as compared to the 8-bit SBoxes. Then coming to the architectural variants, which are options available for us to design an SBox, are the lookup table based, which are already done by the existing works. But the problem here is the designer has no control over the area and performance, because if a table is fitted in the code, the tool automatically maps to the architecture of the device. Then coming to the logic function, we have the logic functions, the Boolean functions, which need to be obtained from the SBox. And the problem here is we have a delay. The delay is more, the critical delay is more in case of gate based design. Coming to the mux based design, which we have proposed in this work, here the delay has been considerably reduced because it efficiently maps with the FPGA architecture. And there are other forms of architecture options like composite field, which can be seen in case of AES, but again the area consumption is more in this case. Coming to the algorithm for proposed for the SBox architecture, here we have the input to be as input bits as I0, I1, I2, and I3. The output functions to be generated are O0 and O1 and O2 and O3. The idea here is to fix the LSB bits as the select lines, and here we have used a 4:1 mux for efficient mapping. And then the logic functions are generated with the help of the MSB2 bits. And after optimizing it, we can minimize it and reuse the minterms wherever possible. Now, coming to the logic functions, from the algorithm, we have generated the logic function. This table 2 represents the logic functions for mux-based design. We see that for the gate-based design, which are obtained directly from the Boolean functions, even if after minimization, we see that the number of literals, if we take the example of O0I, the number of literals has reduced in case of mux-based design, that is from 9 to 6. But in case of also the number of logic operations has also reduced in case of mux based design. Similar observations can be seen for other output functions also. So this is a block diagram. As I said, the logic functions are initially generated and then fed as input to the muxes. Here we require 4:1 muxes to generate the output logic functions. Now, we have chosen FPGA as the implementation platform, and we have implemented all the designs by constraining it to 13.56 megahertz, which is quite appreciable for RFID applications. The parameters are slices, LUTs, and flip-flops for determining the area parameter, and the maximum operating frequency is denoted as Fmax. These are the FPGA devices, and here we see that for GIFT, Midori, and Clean, for the case for mux-based approach, we see that there is a significant reduction in the number of slices due to efficient mapping, and there is a maximum increase in the maximum frequency of operation also. Similar observation is seen for Midori, and for one of the cases for Clean also, we find that the area has been reduced along with the maximum frequency of operation has increased. Coming to the performance, we have calculated the throughput. And the at maximum frequency and also at the RFID frequency, and the power is determined from the tool, and energy is calculated as Fmax. So here we see that the throughput at Fmax has also increased, and we see that the energy has been considerably reduced. Also, for Midori and Clean, we see that there is an improvement in the power best approaches for the said devices. And now we have tried to design a prototype for the clean architecture so that it can be used for healthcare database. The idea here is to embed a security module in the healthcare gadgets or the wearables which we use, which definitely which are used in the consumer electronics, and they are dependent on the RFID frequency. So the idea here is to convert the raw data to a test data and then pass it through an encryption process which will include a lightweight cipher, and then store the data or transmit the data. And this will be possible only with the key present with the authenticated entities. So we have collected the data from the Fitbit data set, and these are the parameters: age, weight. We have taken the input as the plain text as age parameter, and age underscore e, for example, is the cipher text or the encrypted input. So here we have taken the key bit to be fixed, and now we have validated the results in Nexus 4 DDR. And we see here that after the done signal is high, that is the encryption is completed, and we get this output. And if we, this is just the LSB to MSB, so if we do the reverse round, it will be 1100 1101, that is CD, which is obtained in this for identity 1 for in this table. So so in a summary, we can say that the designers has to take care while designing the lightweight ciphers, because there are always trade-offs. And whenever we go for definitely, if we go for more number of rounds, we may improve the security, but again the performance is hindered. Again, if the key bits are increased, definitely the security increases, but we have to take care regarding the area of the cipher also. If, for example, for architecture, if we see, if we go for a parallel architecture, definitely the performance will improve. But again, there can be more area, and this increases the cost. So with this, the designers should take care and should decide which parameter has to be optimized depending on their target applications. So with this,
Please
I can
conclude.
conclude with this, I conclude that the designs, with the conventional designs of modifying the architecture like serial and parallel, instead of doing that, we have tried to modify the S-box architecture, because these are repeated again in the substitution layer, and it significantly affects the area and throughput of the design. And we have also constrained it to 13.56 megahertz so that it is suitable for IoT applications. And the future work is to implement the proposed designs on ASIC platform, and we also intend to construct a lightweight, secure S-box for in the future. So these are the selected references. Thank you. Okay. Yes, algebraic normal form can be used, but again it increases the delay if we go to the micro architectural level. It increases the delay of the design, overall
No,
design.
but that is your conjecture. Have you done it? That is the question. No, what you have to write expressions for the four outputs of the S box, and then synthesize that, and then you will know whether area is required is more or delay is more
Yes,
or
sir.
fault is present.
I have tried that, because this gate based which I showed in this slide, uh, in table 1, the input functions which I was showing, here which I showed is the direct Boolean functions. We have used all the logic gates, mixed gates.
No, no, direct Boolean functions are not optimal because using Karnaugh
Yes,
map you can design 1,000 designs.
yes,
Okay,
sir. Yes,
but
sir.
algebraic normal form is only one solution you get, and that generally people implement because supposed
Yes,
to be the most optimal. Anyhow, don't worry.
yes, sir. But for FPGA, we have moved for these mux based designs.
Okay, okay.
Mhm.
Okay, thank you.